Hi, I'm Richard Newt. I live in Bend, Oregon, and that is in the middle of Oregon. And Oregon is in the middle of, or it's on the West Coast. That's about where I live. So this is a picture of Bend, and here are the Cascade Mountains. And this is the North Sister, Middle Sister, South Sister, and as it appears, is Broken Top. And I live about where this arrow is. So, at any rate, many years ago, managing engineer, world-renowned safety house, told me that safety is an art that takes many years to learn. Well, yeah, that's a big problem, because if it's an art, it's going to be open to interpretation as to what constitutes safety. So I was not too happy with that idea. Safety is learned from the safety standards. I think a lot of us have done this. Writers are the experts, and that's the way things go. But I take a different point of view. I'm a heretic, as you might have known. Safety is an engineering discipline. It's learned by applying the principles of science, physics, and engineering. And we're going to see some of that in my presentation for today. This is the title of the presentation is Hazardous Live and Limited Current Source. And this came up because a colleague asked me what the requirements are for a limited current source, because he had read the standard and had not understood what it was supposed to be. He had a client that insisted that a circuit, that the device that he was evaluating had a limited current source. But in order to define what a limited current source is, we also have to identify what is a hazardous live circuit. What is meant by hazardous live? Well, in order to do this, I looked at TC64 publications. TC64 is entitled Electrical Installations and Protection Against Electric Shock. It's the granddaddy of all the IEC standards and requirements. And its purpose is to lay down basic safety requirements for protection against electric shock for use by technical committees. We'll see that few technical committees pay attention to TC64. Here are the major, or the standards that are really important when it comes to TC64. First one is 1140, protection against electric shock. Next is TS 1201, which is technical specification 1201. It's a guide for the use of conventional touch voltage limits. And finally, we come up with TR technical report 479. The effects of current on human beings and livestock, not too much on livestock, but it tells a lot about human beings, current on humans. So I thought I would discuss the intent of these TC64 publications. 1140, which is protection against electric shock, common aspects. It's intended to give fundamental principles and requirements which are common to electrical installation systems and equipment. It's a basic safety publication intended for use by technical committees. So technical committees are supposed to use this document. We'll see if they don't. But anyway, 1201 provides guidance for the use of conventional touch voltage limits. And it's also a basic safety publication intended for use by technical committees in preparation of standards. Finally, technical report 479 provides basic guidance on the effects of shock current on human beings. And it too has a status of basic safety publication. Well, I looked at a number of standards here, and I started off with, in no particular order, 1010, which is safety requirements for measuring instruments. 601, which is for medical equipment. 950, which is now or soon to be superseded. It's for IT equipment, computers and stuff. 13471 or 1347. Lord Chang put me onto this in his presentation to the symposium in 2012. We'll talk a little bit more about that. 335, which is household equipment. 62368, which is the replacement for 950 and 65, which covers audio, video, information, and computers. Finally, there's the old 65, which is audio, video, and similar electronic safety. Okay, moving ahead. First thing is we need a definition for live part. This comes from 1140, and it's repeated in 335. It's a conductor or conductive part intended to be energized in normal operation, including a neutral conductor. This is an interesting definition. It's a live part because if you follow this definition, the cell circuit as well as the neutral conductor are both live parts. But the 1140 goes on, and we'll see in a moment. It's a special case of a live part is a hazardous live part. So we'll see what the hazardous live part looks like. Definition. It's a special case of a live part, which under certain conditions can give a harmful electric shock. Okay, that's very reasonable. 1010 has a similar definition. It simply says capable of rendering electric shock. That's hazardous live. 950 uses voltage, hazardous voltage instead of hazardous live. And it's a voltage exceeding these numbers you're familiar with, 42.4 volts peak, 60 volts DC. Existing in a circuit that does not meet the requirements for a limited current circuit. That's interesting, but it's what a hazardous voltage is. Finally, we have 65, which says electrical condition of an object from which a hazardous touch current can be drawn. Well, that's a problem. We're going to see that that's a problematic definition, and if hazardous touch current in many standards is 0.5 milliamp, and the body resistance, according to 990, is 2,000 ohms. So if we apply Ohm's law, where the current is multiplied by the body resistance, 0.5 milliamp times 2,000 ohms is 1 volt, which would mean that all under 65, all batteries would be hazardous live. Fortunately, 65 doesn't follow their own definition. That's okay. And we have to look at protective separation from hazardous live, low voltage and low current, and separation of one electric circuit from another by means of double insulation, basic insulation, grounding, or reinforced insulation, classic kinds of stuff. And if we look at 65, it says essentially the same thing, separation between circuits by means of basic and supplementary protection. Okay. And finally, we also have 950, which uses a different word, talks about segregation of accessible parts of limited current circuits from other circuits, shall be as described for cell circuits. So a cell circuit and a limited current circuit are separated, are segregated from other circuits. Doesn't say what other circuits are. My definition for a protective separation is separation of one electric circuit from another, where the separation is such that under both the normal operating conditions and single fault conditions, the separated circuit voltage or current is not hazardous live. Hazardous live, I'm using the definition as we talked about from 1140. Then let's talk about voltage for a few minutes, voltage definitions. Prospective touch voltage. Well, yeah, and it's prospective, it's not actually being touched. So you have voltage between simultaneously accessible conductive parts when those parts are not being touched by a person. Okay. Now, what do you think effective touch voltage is? Well, effective touch voltage is when you're touching those parts. Voltage between conductive parts when touched simultaneously by a person. All right. We can measure touch voltage. And we have prospective touch voltage. In one case, we measure with a voltmeter, it's open circuit voltage. Effective touch voltage, which is from 61,437, which is the other standard, is usually a 50,000 ohm voltmeter. Well, we're going to look at that for just a moment, see what the benefit of that. First of all, if you're measuring prospective touch voltage, you have a 120 volts and 238K resistor. But remember, a voltmeter is infinite impedance, infinite resistance, or close to it. 10 to more than 10 megohms, 10 megohms or more. And that's quite a bit more than 238K. So you measure 120 volts, there's no current flowing through this resistor. There's no voltage drop, so you measure the voltage across this. But if you look at effective touch voltage, you put a 50K resistor across the same thing, and you measure peak voltage as 20.8 volts. So that's still effective, that's low voltage. The voltage between the part concerned, effective touch voltage, the voltage between the part concerned and the accessible part is measured, the measuring circuit having a non-inductive resistance of 50 ohm, 50,000 ohms. Okay. The part is concerned as a live part if the voltage is more than 34 volts. Peak. 34 volts. Well, let's look at this. Change the resistor here, so it's 190K, 50K, 240K altogether. That should be half a milliamp. So if we look at Ohm's law, I is equal to E over R. 34 volts peak over 50,000 ohms is 0.68 milliamps peak, which is about 0.7 milliamps peak, which is about half a milliamp RMS. So it's one way of doing things. We don't do it, usually don't do it that way, but it can be done that way. So why 25 volts? If we look at 479 again, small surface area, hand to hand and dry at 25 volts, the body impedance is anywhere from 91,000 to 317,000 ohms. At 50 volts, it's 75,000 to 250,000 ohms. That's interesting. Back in 1956, Dalziel and Soglia published a paper. And in that paper, they said human tissue has a negative resistance characteristics. That is, the body resistance decreases with both increasing current and with increasing time of contact, with the result that doubling the voltage more than doubles the current. Here's the curve taken from 479 figure 6. Surface areas of fingertips, current path from tips to the right to the left forefinger. And this is what he measured, what was measured on one body. This is touch voltage this direction and body impedance this way. And if we entered the voltage that we measured, 34 volts peak, is 50,000 ohms. Well, this is RMS. We can't do that. 34 volts peak is about 24 volts RMS. And if we go up here and look at this curve, it's about 70,000 ohms. So the body is about 70,000 ohms at 34 volts peak. That's okay. You aren't going to get very much current through there. But 1347 is contradictory to 1140. And where 1140 says a live part is a conductive part tend to be energized in normal operation. And 1347 says the part concerned is a live part of the voltage of more than 30 volts peak is measured. So it's contradictory. CLV and SCLV voltage definitions. We'll look at these for a moment or two. And 1140 says this any voltage which not exceeding the relevant voltage limit specified in 1201. Okay. And safety extra low voltage is what? Is defined in terms of ELV. An electrical system which the voltage cannot exceed ELV limits under normal conditions and under single fault conditions. I'm not worried about this other part. It's got to have protective, in essence, protective separation between live parts and non-live parts, or between live parts and the subsystem. For the purpose of this presentation, I'm using the term unlimited voltage circuit. So in order to contrast it with a limited current circuit, which is what we're after. So a limited voltage circuit is a circuit that's so designed and protected under both normal and operating conditions. Normal operating conditions and on single fault condition, the voltage is not hazardous live. And we'll do the measurements. The ELV is measured with a voltmeter. The safety extra low voltage is also measured with a voltmeter, plus the measurements of the protective separation. So a limited voltage circuit is a circuit that is so designed and protected that under both normal operating conditions and single fault conditions, the voltage is not hazardous live. All right. So here we have the hazardous live circuit. And we have protective separation between the two, between here at this point. And we have the lower than ELV. This may very well be the secondary of a transformer. And this may be the primary of the transformer. But you have to have protective separation. The voltmeter measures the voltage at less than ELV. Okay. Now let's look at current. Current definitions from 1140. Limited current source is a device supplying electrical energy in which an electric circuit with protective separation from hazardous live parts. Okay, that's from 1140. And we have definition from the IEV, the International Electrical Technical Vocabulary, which is touch current. It's electric current through a human body. Okay. But leakage current, which we use both these terms as meaning the same thing, but if you look at 1140, leakage current is electric current in an unwetted conductive path. Unwetted conductive path, okay. And protective conductor current, taken from the same standard, 1140, the current flows in a protective conductor. Be careful about this. We'll talk a little bit more about this. We wonder, we wonder, but we put a lot of emphasis on the current and the protective conductor. We'll talk a little bit more. So a limited current circuit is a circuit that is so designed and protected that on both normal operating conditions and in single fault conditions, the current that can be drawn is not hazardous live. That's from 950. I changed this, it said hazardous, and I changed it to say hazardous live. So the current measurement, limit current source, is measured with a body impedance current meter. Touch current is also measured with a body impedance current meter. Now the body, this one, limit current source, you have to measure the separation characteristics also. Leakage current, if we follow the definition from 1140, leakage current, you would measure it with an ammeter, a zero impedance current meter. Protective conductor current, because it's doing what it's supposed to be doing, and you measure the protective conductor current with an ammeter. Straightforward. However, if we're going to compare all of these things with touch current, which is a limited current source, it's a special case of touch current as protective separation. Leakage current is not touch current if we follow the definitions in 1140. Protective conductor current is not touch current, but may include leakage current. However, if it's open protective conductor, open is not a current. I shouldn't have put that in there. So an open protective conductor is touch current. So here's hazardous live circuit we had once before. We have protective separation, and we have the secondary circuit, but this time the voltage is greater than ELV. So we measure this thing with the peak milliammeter, and it's 2 kiloohms. We put 2 kiloohms across this thing, and we measured the current. So let's look at what the standards say. The first standard says limitation of voltage at 601 is the medical standard. Limitation of voltage current, and don't worry about energy. Accessible parts, if voltage is higher than the limits specified, don't worry about what they are. Leakage current limits referred to. So if we look at 601, if the voltage exceeds the LV, the current must not exceed the current limit. Okay. We look at 1010 for test and measurement equipment. Limit values for accessible parts. Voltages above the levels of A, ELV, are deemed to be hazardous live if any of the levels of B or C. B is the touch current limit. Okay. So it's hazardous live if the voltage exceeds the LV, the current exceeds the current limit. All right. Look at 62.368. Yeah. We have either the prospective touch voltage or the touch current does not exceed the limit for ES2. We'll talk a little bit more about that, but we aren't going to address that. So either the protective touch voltage or the touch current does not exceed the limit. That's okay. We look at 335. A part is supplied at safety extra low voltage. It's not considered to be live if the part is supplied at extra low voltage, or the part is separated from live parts by a protective impedance. That's interesting. If a protective impedance is used, the current between the part and the source shall exceed some value, some level. We're not going to concern ourselves with the actual values. It's not live if the voltage does not exceed the LV or the current does not exceed the limit current. That's okay. All of these are very similar. A part or contact of a terminal is hazardous live if the open circuit voltage exceeds this, and if the voltage limits are exceeded, parts B to D apply. And it talks about touch current. Touch current exceeds the following voltages, or the voltage values rather. Their voltages are measured at 990. So hazardous live if the voltage exceeds the LV and touch current exceeds the current limit. Okay. Finally, we get to 950, which defines hazardous voltage as exceeding ELV and does not meet the requirements of limited current circuit. So hazardous voltage exceeding ELV and does not meet limited current. So we all across here, we have voltages reference to ELV, and we have current reference to limited current. So hazardous live, prospective touch voltage exceeds ELV, and touch current exceeds touch current limits, whatever they have to be. And if we turn over to 1347 standard, touch voltage exceeds 34 volts peak. That's so thing. In any case, it's always the same. Exceeds ELV and exceeds touch current. That's hazardous live. Limited voltage source. All circuit conductors utilize protective separation with respect to hazardous live circuit conductors. Open circuit voltage does not exceed ELV, but we don't have any limit on the current. So we can summarize this as a limited voltage source itself. It's got protective separation. Does not exceed ELV, it exceeds touch current. It can exceed, we don't care what the current is. A limited current source also has the same criteria with regard to protective separation, but its open circuit voltage can exceed ELV limits and the current does not exceed touch current limits. So it's the same thing. Protective separation. This one does not exceed ELV, but does exceed ELV. Does not exceed touch current. That's the criteria. So we can now talk about electric shock effect on the body as a function of both voltage and current. If the voltage is low, then no electric shock. If the current is low, then no electric current, regardless of voltage. Regardless of current, you can touch a car battery, 12-volt car battery, with impunity. Okay, got lots of amps behind it. And if both the voltage and the current are high, then electric shock is likely. So here's our final explanation of what these things look like. Hazardous live exceeds ELV and exceeds touch current. But then you have a limited current source, limited voltage source. You have to have protective separation between them. So you have protective separation. The limited current source exceeds ELV but does not exceed touch current. The limited voltage source does not exceed the limited ELV but can exceed the touch current. And does it require protective separation between these two? Well, you find out by applying Kirchhoff's voltage law to their circuit where these two are connected together. So a limited current source is the current equivalent to a limited voltage circuit. That's the clue. Current equivalent to a limited voltage circuit. So practice, we'll take this and apply these ideas. You've all seen these things, these power supplies. And the schematic looks something like this. This is the primary circuit, protective separation, and the secondary circuit. Across protective separation, there's always an impedance of some sort across that separation. I picked some values here. We'll talk about more about this a little bit. But they can be any. But they're pretty high. And here is the primary and the rest of the primary circuit, 120 volts. And this is a 2-wire system. Well, it doesn't connect to the ground. So the primary circuit, the hazardous live circuit, is this one. Goes from 120 volts, goes into the switching mode power supply to the transformer, and returns back to the 120 volts. The output, here's the 5 volts output to the load, wherever load is, and returns that way, and has protective separation. And if we measure the voltage, we'll measure 5 volts DC. Okay. The voltage is low, no electric shock effect regardless of current. However, this thing has a limited current circuit by the red arrows. So the current comes through here, goes across the impedance, the protective separation. It's a pretty small current. Goes through the transformer, may not be, well, depending upon how the circuit out physically is laid out, returns this way, returns to the source. All right. So we still have our 5 volts. If the voltage is low, no electric shock, regardless of current. There's none of this voltage appears across there. However, we put a voltmeter of either pole, 5-volt circuit, we're going to read about half the mains voltage, half of the 120. Why? If we look at this, the current goes through these resistors. Assume this is a short circuit for the moment. And so it goes through these resistors and returns. It's going to be about half voltage since both of these are the same. However, if you put the current on, measure the limited current with a 2K resistor, you read 0.35 milliamps peak. Most of the current goes through the current meter, and a little bit of the current goes back to the source that way. All right, if the current is low, and no electric shock effect regardless of voltage. And we can put 2 voltmeters on this thing at the same time, measure 5 volts DC, the output, which is where all the business is, and 60 volts RMS, half the voltage. Voltage is low, no electric shock. And the current is low, no electric shock regardless of voltage. Finally, if this thing is grounded through other equipment, all the limited current circuit passes this way, still have 5 volts DC. You have no voltage for the spectrum ground. So the voltage is low, no electric shock effect regardless of current. And that's it. That's the end of hazardous lag and limited current source. The limited current source is the equivalent of a cell limited voltage source.